Hello everyone. This is Xingjian Zhen from UW-Madison. In this video, we will provide a high-level overview of the main challenge and rationale that motivated our work. We will cover the main simplifying assumptions that enable designing an efficient scheme for certified radius maximization by propagation of covariances. Our overall goal is to provably certify the robustness of the network. This is different from the problem setup that several papers study where one wants to train robust networks via adversarial samples. In that setting, the models are not required to certify the robustness of the network as we do here. First, let us consider a two-class classification problem. The decision boundary shown here is from a pre-trained base classifier f-theta. The goal is to certify that for a given x shown as black dot, we cannot find any adversarial point shown as a red dot within some L2 norm ball of radius delta. If x is far away from the boundary, for the delta perturbation shown here, the perturbed data will also be classified as cat by f-theta. However, things get worse as x gets closer to the boundary. Here, as we can see, it is much easier to find a perturbation delta applied to x where the classifier makes a mistake. But consider a small change. Instead of directly considering the base classifier, let us consider a smoothed classifier where we average over some neighborhood. Now, since x plus delta has more neighbors that also have a label cat, the classifier will be smoothed. In this smoothed case, x plus delta will now have the same label as x. The boundary of the smoothed classifier g theta will be smoother than the base classifier f theta. Cohen and colleagues in paper at ICML last year studied this problem and provided theoretical guarantees that within some L2 norm ball, there cannot exist any adversarial samples for the smoothed classifier. This idea only gives us a way to generate a robust smoothed classifier when given a pre-trained base classifier, but the proposed ideas do not directly train a robust base classifier. As the smoothed classifier will need to smooth over some neighborhood, one approach can proceed as follows. We can sample some perturbed samples around the input x to see what the output of the network will be. We first sample an epsilon and add it to the input x. We pass it through the network. By doing so, we can obtain the output of the network u theta of x. Now, we repeat. Then we sample another epsilon. And pass it through the network again to have another u theta of x. And so on, we continue sampling. If we sample enough epsilons, we can have the region of where the output can be perturbed. Intuitively, if more than half of this region is classified correctly, the smoothed network will be robust. Since counting is non-differentiable, Jai and colleagues in a nice paper this year called Macer showed how a soft counting can be used to train a robust base classifier. This idea motivates our paper. Let us see how this sampling procedure would work. Clearly, the sampling should well represent the perturbation region. But by the unscented transform, in the worst case, it would require 2n+1 samples for an n-dimension data to make an accurate estimation. For 2D data, it requires 5 samples. For 3D data, it requires 7 samples. But for ImageNet data, the dimension is too high that requires more than 300,000 samples. Yes, this is the worst case. If we assume that the image data lies in some low-dimensional manifold which can be identified, the number of samples will depend on the dimensionality of the manifold, that is, the true degrees of freedom of the data. But even for CFAR-10 data, which is only 32 by 32 by 3 dimensions, it at least lies in dimension 64. For ImageNet, the dimension would be much higher than 64. On the other hand, consider the following situation. If we can characterize the perturbation distribution directly instead of using samples, we can potentially break the dependency of the dimension. So, can this strategy work? Let us first look at one pixel of the input. If we track all the perturbation epsilon and visualize it on the axis, since epsilon comes from a normal distribution, we get a distribution of the perturbed data sample x, shown in red. What will be the mean of this distribution? It will be the original value of x, which is 1. The variance will be the variance of epsilon. Now let us go back to the network and see what happens. We can calculate all the distribution of the input pixels. Now, if we can track this distribution through the network, especially while avoiding sampling, we can, in this case, also obtain an estimate of the distribution of the output u theta x, similar to what we achieved with the sampling strategy. A benefit of this method is that it does not depend on the input dimension. It will require only one feed-forward pass for all types of data. It does not care whether the data is 2D or much higher dimensions as in ImageNet. So what is the challenge of tracking the distribution exactly? Why shouldn't we do this? Well, this approach runs into some difficulties. Let us look at the last layer. In the last layer, we want to calculate the distribution of u theta x, so we will need to compute the sigma I. What do we need to calculate sigma I? Well, it depends on quantities in the second last layer. So if we write down the equation of sigma I involving terms in the second last layer, as shown here, it will require 3 covariance matrices sigma and 3 cross-correlation matrices E, highlighted in blue and red. We can continue backtracking this style of calculation, asking what we need to calculate the terms in the second last layer. In the second last layer, to compute the sigma I-1, which highlighted in orange box here, it will require to compute 3 covariances and 3 cross-correlation matrices in the third last layer. For the cross-correlation term in the second last layer, which is highlighted in green box, it will require 4 covariance matrices and 6 cross-correlation matrices in the third last layer. Things will get much worse as the network grows deeper. Actually, it will require k-1 times q plus 1 number of sigma matrices and many more cross-correlation matrices in the q plus 1 last layer. As we can see, the most difficult part is the cross-correlation term E. We need to find an efficient way to deal with it. Let's look at a 2D example where the sigma of x and y to be 1 and E is -0.6. If we can use 2 independent random variables to upper bound the dependent x and y, we can leave the cross-correlation term out. More formally, we consider 2 Gaussian random variables. Let us assume that we don't know the cross-correlation E between x and y. Instead, we only know that the correlation coefficient is less than some value R max. As shown here, when E varies, the probability ellipsoid changes. We will need a mechanism to the distribution to have covariance B shown here. We can bound all the ellipsoids using this new red ellipsoid. We can see empirically this behavior for different Rmax values here. When Rmax is small, for example 0.01, the upper bound will be very close to all the ellipsoids. As Rmax increases, the upper bound is larger, but still as tight as possible. Using this strategy, we can upper bound and substitute all the cross-correlation matrices in the network as long as we can estimate Rmax. Then, the overall computation cost will be linear in the depth of the network, which will be feasible to deal with. The detail of how to efficiently track the covariance matrices through the network requires a few additional mechanical changes in the different network modules. The details of these adjustments, for all 4 types of layers, can be found in our main paper and the supplement. Our results show that these simplifications are acceptable and can lead to a faster robust training than a sampling-based method, and offers similar test accuracy as alternatives, especially if the network is not extremely deep. This provides an efficient strategy for certified radius maximization for robust training of deep neural network models and vision. Thank you for listening.